This lesson is about systems of linear equations. A linear system of equations is a set of two or more equations and any number of linear variables that must be solved simultaneously. A small linear system is one that contains two equations and two variables, and a large linear system contains three or more equations or variables. A solution to a linear system is an xy coordinate pair that satisfies both equations simultaneously. Consider the system x plus y equals 4 and negative 2x plus y equals 1. Notice that both equations are linear equations and they're grouped together by the curly brace, which is customary notation to define a system of equations. The coordinate pair 2, 2 is not a solution, since if I plug in 2, 2 into both equations, it doesn't satisfy both simultaneously. So for instance, in the first equation, if I take x plus y equals 4 and plug in the point 2, 2, then I have 2 plus 2 equals 4, which works out. So it is a solution to the first equation, but when I plug it into the second equation, negative 2, when I plug in 2 for x, that's that, plus 2 equals 1. Negative 2 times 2 is negative 4, plus 2, this is not equal to 1. This is actually negative 2. So it doesn't work out as a solution to the second equation. So the coordinate pair 2, 2 is not a simultaneous solution. It's not a solution to the system. Let's try another point. Let's try 1, 3. In the first equation, x plus y equals 4. This certainly works out because 1 plus 3 does in fact equal 4. In the second equation, negative 2x plus y equals 1, we would have negative 2 times 1 plus 3, and that should equal 1. So this is negative 2 plus 3, which does in fact equal 1. So 1, 3 is a solution to the system. And this raises a question. Are there more solutions? What's special about this point? To answer that, let's take a look at the graphs of these two equations. So if I have x plus y equals 4, it's going to be easier to graph it in the form y equals negative x plus 4, just moving the x to the other side of the equation. Similarly, negative 2x plus y equals 1 will be easier to graph in the form y equals 2x plus 1. So the first line has a y-intercept of positive 4 and a slope of negative 1. So the equation of that line looks like this. The other line, 2x plus 1, the y-intercept is 1 and the slope is 2. So if I go up 2 and over 1, then up 2 and over 1, or down 2 and back 1, in order to get a few additional points, I come up with this graph right here. The coordinate pair that was a solution was the point 1, 3. If you'll notice, that happens to be the intersection point between these two curves. So the rule is a point that solves a system of equations simultaneously is an intersection point of the graphs of the functions. In order for two graphs to have the same, to share the same coordinate pair, they have to have an intersection point. The x and the y has to be on both graphs at the same time. To answer the question, are there more solutions? I think it would be obvious to say at this point, no, because there's no way that two lines could ever intersect at more than a single point. So there would only be one solution to this system. Which leads us to three different cases of solutions for small linear systems. The first case is where we have one solution to the system. So similar to the example we just performed, when the two lines intersect at a single point. And when the lines intersect, there's going to be one solution, and we would always express that solution as the coordinate pair x, y. Another case is when there are no solutions. If there are no solutions, then your lines would never intersect. This occurs with parallel lines. So whenever your lines are parallel, there is no solution. Occasionally, you will see the symbol for the empty set being used, which is the 0 with the slash through it. And that's appropriate way of expressing that there is no solution to a system, as well as stating there is no solution. The third case is when there are infinitely many solutions. When there are infinitely many solutions, the two lines in question happen to map out the exact same set of points. So the two lines are effectively the same line, and in order to express the solution, we must parameterize the solution. And I'll show you through an example what that looks like when we get to that case. In order to solve systems of equations, we have two methods that are generally used most often with small linear systems. First is the substitution method, and second is the elimination method. Let's look at both of these methods. The substitution method, the steps involved here: first, you solve one equation for either variable, and you get a choice as to which one you want to pick. And generally, you're going to choose an equation that has a variable with a coefficient of +1 or -1. Then you're going to substitute this into the other equation, which will reduce you down to a single variable, which you can solve for that variable. And lastly, use what you found for the first variable to solve for the remaining variable. Let's walk through an example so you can see how this works. We already know the solution to this system is the coordinate pair 1, 3. Let's use the process of substitution to see how we would have solved it algebraically. So I choose one equation and solve it for one of my variables. I'm going to choose to take the first equation and solve it for x. So x equals 4 minus y. I could have as easily solved the first equation for y, or even the second equation for y. I probably would have steered against solving the second equation for x because dividing both sides by -2 would result in fractions in my problem. Now, since I have x equals 4 minus y, I'm going to use this in the next equation. So the next equation is -2 times x plus y equals 1. I'm going to take what I know x is equal to in the first equation and plug that into the x in the second equation. So I end up with -2 times the quantity 4 minus y plus y equals 1, which may look more complex than what I started with, but the advantage is there's only one variable remaining in the equation that I now have, and I can solve for one variable. So let's come up here and do that. First, I'm going to distribute the -2 into my parentheses, which would give me -8 plus 2y plus y equals 1. Now I have 2y plus y. These are like terms and can be combined into 8 plus 3y equals 1. I can add 8 to both sides, which results in 3y equals 9. And if I divide both sides by 3, I determine that the value of y is equal to 3. Knowing that, I can go back to any of the original equations and plug in this value of y that I've discovered in order to come up with the value of x. So I'm going to go back to this equation right here and say x is equal to 4 minus 3, so I'm plugging 3 in for y, which results in x equals 1. So my solution to this system is the coordinate pair 1, 3. Let's look at another example. (2x minus 3y equals 5, and (x plus 3/2 y equals 2). In this equation, I'm going to choose the second equation, and I'm going to solve it for x, simply because all the other variables would result in having fractions throughout the problem. So (x) is equal to (3/2 y plus 2, once I subtract the term (3/2 y over). Then I divide everything through by -1, so x equals 3/2 y minus 2. Now I'm going to use this to substitute into the other equation. So the other equation is 2x minus 3y equals 5. My x is going to transform into 3/2 y minus 2, and nothing else gets affected at this point. Now I'm going to distribute the 2 into my set of parentheses. So this will result in 3y minus 4 minus 3y equals 5. The next step, if you'll notice, I have a positive 3y and a negative 3y. Those cancel each other out, leaving me with -4 equals 5. There are no variables remaining in the equation. All the variables have canceled out. And certainly, -4 does not equal 5. This is a contradiction. And when you have a contradiction, that's an indication that there is no solution to this system. So, essentially what that's telling me is that the original two lines were parallel to one another. So there's no solution. Let's look at the elimination method. The steps to perform here are, first, one or both equations is multiplied by a constant so that when added, a variable cancels out. Then we add the equations and solve for the first variable. And finally, we use that to solve for the remaining variable. For small linear systems, this is generally a little bit faster than the substitution method. And for me, it is my preferred method. Now, I want to choose one of the equations to multiply it by a constant so that when I add it to the next equation, I get a variable to cancel out. For instance, I'm going to take the top equation and multiply it by 2. So if I take this top equation and multiply it by 2, I will get 2x plus 2y equals 8. And with that, I will combine it to -2x plus y equals 1. I'm going to now add these two equations together term by term. So -2x and +2x cancel out. 2y plus y is 3y. 8 plus 1 is 9. And now all I have to do is divide both sides by 3 so that y equals 3. And I already have the first solution. Now I just have to come up with the other coordinate for the solution, and I can go back to any equation at this point. So x plus 3 is equal to 4. So if I subtract 3 from both sides, I discover that x is equal to 1, so that my solution is the coordinate pair 1, 3. So the original system that we worked with, it doesn't matter if you are using the substitution method or the elimination method, you'll get the same result in the end. Let's try one more example. So we did this example with the substitution method and discovered that there was no solution. Let's see what that looks like when we use elimination. So I think what I'll do is multiply the bottom equation by 2. So the top equation stays the same. 2x minus 3y equals 5. The second equation becomes -2x plus 3y equals 4. When I add these together, the x's cancel and the y's cancel, leaving me with 0 equals 9. And this is a contradiction, which tells me there is no solution. We have seen examples that lead to a unique solution, and we've seen an example that leads to no solution. Let's look at the next example, which leads to a solution that must be parameterized. And in that case, what do we need to do to present the final answer? So, parameterizing a solution. If you end up with a statement such as 0 equals 0, this is not a contradiction, but an indication that both equations are equal and you must parameterize the solution. The process for parameterization is to choose either variable to be arbitrary. You can choose the x or the y to be arbitrary. Then solve the equation in terms of the arbitrary variable, meaning the other variable will be by itself. And finally, express the solution as a point. This is generally easier to do than it is to state how to do it. Let's look at an example. The system negative x plus 2y equals 5 and 3x minus 6y equals negative 15. In order to solve this, I'm going to use elimination. And I'll start by multiplying the top equation by 3 so that it becomes negative 3x plus 6y equals 15. And the bottom equation is 3x minus 6y equals negative 15. When I add these together, the 3x and negative 3x cancel out. The 6y and negative 6y cancel out, so I'm left with 0 on the left-hand side. But also, the positive 15 and negative 15 cancel, and leaves me with 0 on the other side of the equation. So essentially, what this is telling me is that these two lines are the exact same line. So I must parameterize the solution. In order to do that, I'm going to choose one variable to be arbitrary. I'll choose y in this case, which means I'm going to get x by itself. So if I have negative x plus 2y equals 5, and I can use either equation at this point because both equations are the same. If I multiply the top equation by negative 3, it results in the bottom equation. So it doesn't matter which one I'm using here. Just pick the simpler of the two. I'm going to get x by itself in this equation. So negative x equals negative 2y plus 5. And if I divide both sides by negative 1, I get x equals 2y minus 5. Now, with this, I can express my solution as a coordinate pair. And that coordinate pair looks like this. So the y variable I chose to be arbitrary. So y is just y. It's just itself. The x variable is defined by an equation in terms of y as 2y minus 5. Now I have a coordinate pair that represents every single point on this line. So for any value that I choose for y, the value 2y minus 5 gives me an x coordinate that exists on the line. So I'm representing every single point. But you can choose x or y to be arbitrary. So it really doesn't matter how you go about this. I could choose the other variable to be arbitrary. I could choose x to be arbitrary. And if I start with negative x plus 2y equals 5, then I just need to solve the equation for y. So I'll add x to both sides, which gives me 2y equals 5 plus x. And then if I divide both sides by 2, and I'll reorder 5 plus x into x plus 5 divided by 2, which could also be expressed as 1/2 x plus 5/2. then the coordinate pair of the solution would be x was arbitrary, so now x is by itself. Y is 1/2 x plus 5/2. These two solutions lead to the exact same line. It's the same representation, a different representation of the exact same line. So you can choose either one, but don't answer using both. I've seen students try and express, and let me write this in red because it's wrong. Well, 2y minus 5, comma, 1/2 x plus 5/2. So they do the work for both sides and combine the results into a single point, but this does not give an arbitrary variable, so it doesn't map out the correct line. Next, we're going to see what we need to do when we deal with large systems of equations. Solving large systems with substitution or elimination is not difficult, but there is a lot of bookkeeping involved. Another method that takes care of the bookkeeping for you by using matrices is the Gauss Jordan method, which is based on the following elementary row operations. And by the elementary row operations, you are allowed to interchange any two rows, multiply or divide a row by a non-zero constant, and add a constant multiple of any row to any other row. These are the same rules that guide us in using the elimination method. They're just generalized for the use of matrices, which means we have to change our system into what's called an augmented matrix, which is a matrix containing only the coefficients of this system of equations. So, for example, if I have a system of equations such as this, x plus 2y minus 4z equals 12, 3x minus y equals 15, and 9x minus 2y plus 5z equals 4. So now I have 3 equations and 3 variables, so that's a large system. The augmented matrix is a matrix of the system of equations coefficients. So the first column in this matrix makes up everything multiplied by x, so all the coefficients of x. The second column is all the coefficients of y. The third is all the coefficients of z. And the last is the constants. So each row represents the coefficients of an equation. So the top row of this matrix would be 1, 2, -4, and 12. Generally, we represent the equal sign in an augmented matrix with a elongated bar. For the second equation, I have 3x minus y equals 15. So the coefficient on the x is 3, on the y is -1. There is no z variable, so its coefficient is 0, and the constant is 15. In the last equation, 9x minus 2y plus 5z equals 4. The coefficient on x is 9. The coefficient on y is -2. On z is 5. And the constant is 4. To solve an augmented matrix, you must use the elementary row operations to get your matrix in either what's called reduced row echelon form or row reduced echelon form. And I'm pointing out the difference here because on the calculator it makes a difference. Reduced echelon form looks like this. your main diagonal is all ones, and everything underneath your main diagonal is zeros. The main diagonal is this right here. In row-reduced echelon form, the main diagonal is all ones, and everything else is zeros. And the idea in row-reduced echelon form is if everything in the first column is multiplied by x, everything in the second column is multiplied by y, and everything in the third column is multiplied by z, then if you transform this into a system of equations, you have x equals c1, y equals c2, and z equals c3, so that your solution is the coordinate triple c1, c2, c3. In reduced echelon form, there's still more solving to do, but in row-reduced echelon form, the solution is just as stated. So it's more advantageous to go ahead and express it in row-reduced echelon form rather than just simply reduced echelon form. Ultimately, we're going to allow the calculator to solve these, so the next example shows only the calculator method. The reason we're choosing to use the calculator here is because these row operations, although relatively easy to apply, they're very easy to make mistakes with, because when you have to interchange any two rows, that's relatively simple. You just swap two rows. No mistakes generally occur there. But when you have to add a row, add a constant multiple of one row to any other row, there's a lot of addition and multiplication that has to be done. It's very easy to miss a sign and mess up your matrix. It's a very error-prone system. However, it's great for computers, and we're going to allow our calculator to do it for that reason. So let's see how the calculator would solve this large linear system. In order to use the calculator, we have to learn a new menu set. That is under the matrix key, which if you look at the x to the negative 1, that above it has the word matrix. In my calculator is yellow. In your calculator it will be the same color as your second key. Now with that, I'll hit second and x to the negative 1 to get into the matrix menu. This is where I find all the different operations that I can do for matrices within the calculator. The first thing you'll notice is there's a limited number of matrices that you can define in your calculator, and this is where you would define them. But I want to edit one of those. So I'm going to edit matrix A, and it tells me that I need to define the size of the matrix. The size of a matrix is defined by a number of rows and a number of columns. So the number of rows that we would use here is equal to the number of equations. The number of equations. So in my case, I have 3 equations. So I put 3 in for the first number. The next value is the number of columns that you want in your matrix. The number of columns is going to be the number of variables plus 1. And the reason it's plus 1 is because you need a column for the constants as well. So I have 3 variables and add 1 to that to get 4. Now I can start entering the augmented matrix. The augmented matrix is going to look like 2, 1, 1, 9, negative 1, negative 1, 1, 1, 3, negative 1, 1, and 9. That's what I'm going to enter into matrix A in my calculator. 2, 1, 1, and it will automatically scroll over to the fourth column that we can't see initially, then 9. Then it scrolls back to the first column. Negative 1, be careful to use a negative instead of a minus. Negative 1, 1, and 1. 3, negative 1, 1, and 9. Now that I've entered my matrix, I need to tell the calculator that I want to solve this matrix as a linear system. In order to do that, I'm going to quit out of the matrix editor by hitting second and mode. This brings me back to my home screen. Now I'll go back into the matrix menu, so second and x to the negative 1. This time I want to do some math with it. And this list is all the different types of mathematical operations you can do with your matrices. Options A and B are REF and RREF, which stands for reduced echelon form and row reduced echelon form. And as we just discussed, row reduced echelon form is the better option of the two. So I'll hit enter, and it waits for me to tell it which matrix I want to do the row reduced echelon form on. So if I hit second in matrix, then I want matrix A. So I'll highlight 1 for matrix A, press enter, and enter one more time, and it will run the function row reduced echelon form, which gives me a new matrix which looks like 1, 0, 0, 2, 0, 1, 0, 1, and 0, 0, 1, 4. This is telling me what my solution is. Since I have the main diagonal as all equal to 1 and everything else in the part of the matrix that doesn't include the constants is 0, then I know my solution is the coordinate 2, 1, 4. This is the x, y, and z coordinate triple that solves my original system simultaneously. I could show by plugging in each x, y, and z coordinate into each linear equation, and it would satisfy every single one of them. If I were to plug the solution, the coordinate triple 2, 1, 4, into each equation, it would satisfy each equation with those coordinates. So it solves the entire system simultaneously. Now, since it has 3 variables, this is actually a 3-dimensional system. And it's easy to visualize a 2-dimensional system because we're so very trained as to how to graph lines in 2 dimensions. I want you to see the relationship of how these coordinates, how this solution works into this system. But we have to jump into 3 dimensions. And you don't need to be able to do that on your own. I just want to graph it for you and show you what it looks like. And that way it'll help you to understand the concepts of what you're doing. Each of these equations represents what's called a plane in 3 dimensions. And a plane is a large flat region that's tilted. So I'm going to graph each of these planes and the point 214 so you can see really what's happening here. Okay, so now I have graphed all 3 planes in 3 dimensions along with the point that I've labeled A as the coordinate triple 214. Each individual plane is just a large flat region that is tilted. And you can sort of see each one, although it's a little bit difficult to see them individually because there's 3 overlapping. If I rotate it, it might make it a little bit easier to see that that one particular point is where all 3 of those planes happen to cross each other. So that is the coordinate of intersection for all 3 of those planes. So that's why this particular system has a unique solution. Next, let's take a look at a system such as this. What I'm going to do is create an augmented matrix and enter that augmented matrix into the calculator. Generally, you'll find it's simple enough to come up with the augmented matrix and enter it directly into the calculator without having to write it down. So that's what I'll do. I'll edit matrix A, which still needs to be 3 by 4. I still have 3 equations and 3 variables plus my constants. And I'm just going to enter the new coefficients of this system. So 1, 3, -3, 4 for the first equation, which was x plus 3y minus 3z equals 4. The second equation is 2x plus 9y equals 7. So I'll enter 2, 9, 0, since the z variable doesn't exist in this equation, and 7. And for the third equation, which is 2x plus 5y minus 8z equals 9, 2, 5, -8, and 9. Next, I'll quit out of the matrix editor and go back into my matrix menu and find the function RREF. And you just want to be careful to make sure you're using RREF as opposed to REF, because REF there's still a little bit more solving that needs to be done. Then I'm going to do this on matrix A, press enter, and I come up with 1, 0, -9, 0, 0, 1, 2, 0, and 0, 0, 0, 1. This is a contradiction, because if you'll notice, if I change this into a system of equations, it would appear as x minus 9z equals 0, which is a strange result, but it's not a contradiction. Similarly, y plus 2z equals 0 is not a contradiction, but in the last equation, 0 equals 1. That's definitely not a true statement. So therefore, this system has no solution. And again, I'd like to help you visualize why there is no solution. So let me graph these in 3D and bring that up for you. Okay. So it's a little bit harder to see that there is no solution, but if you look at it from different angles, it in fact turns out that there is no solution. There's no single point where all 3 of these planes intersect each other. So that's why there's no solution to this system. And it looks like somewhere close to the origin there might be a solution, but if you plug in different points around there that are possibilities, you'll quickly find that none of them actually work. So there's no solution to this system. Let's look at another example. In this next example, I want to do the same thing, take my system, convert it into a augmented matrix, and enter it into the calculator. So a 3x4 system, once again. My coefficients for the first equation, which is negative x plus 25y minus 33z equals 7, will be negative 1, 25, negative 33, and 7. For the next equation, which is 8x minus 8y plus 16z equals 10, would be 1 minus 8 plus 16 and 10. And the last equation, which is x plus 26y minus 18z equals 44, would be 1, 26, negative 18, and 44. When I go to solve this, I'll quit out of the matrix editor, second in matrix, and then find the function RREF. And I want to perform that on matrix A. I come up with 1, 0, 8, and 18 for the first row, 0, 1, negative 1, 1 for the second row, and the last row is all zeros. So essentially, I have a system that, if I change into a system of equations, forms no contradiction. So I have x plus 8z equals 18, and y minus z equals 1, and the last would be 0 equals 0, which is not a contradiction. So this is a perfectly valid solution. What this means is I have a system that I need to parameterize the solution. And z, since it appears in both equations, z is my free variable. And what I'm going to do is express my solution as this. I'll first change each equation into x equals and y equals, respectively. So x equals negative 8z plus 18, y equals z plus 1, and then z, since it's a free variable, since it's arbitrary, I just let it be equal to z. So my solution, parameterized, looks like this. X is negative 8z plus 18, y is z plus 1, and z is just z. So that is the solution to the system. Visually, what's happening here is when I draw these three planes, they aren't just intersecting at a single point, they're actually intersecting along a line. And that line looks like this. Right along here, at every single point, these planes are intersecting along that line. So visually, that's what's happening when you get these infinitely many solutions in 3 dimensions. But again, let me point out that knowing what happens in 3 dimensions is not what's the main purpose of this lesson, and it's not the main objective. The thing you need to be able to do is, for large linear systems, use the Gauss Jordan method through the calculator in order to either state what the solution is, identify that there is no solution, or parameterize the solution when need be. So I just want you to be able to visualize what's happening, and that's the only reason I'm graphing these. And visualizing these will help you understand what's happening in this particular example. Here I have 3 variables, but only 2 equations. If you think about this visually, I have 2 planes that are going to intersect. And no matter how those planes intersect with one another, there's never going to be a single unique solution. But there is always going to be a line of intersection, because there's not a third plane to say that there would be no solution or that there would be a single solution. So if you only have 2 to interact with each other, then certainly you're going to have to end up parameterizing in the end. So let's watch what happens as we go through the steps of solving. So under the matrix menu, I'm going to my matrix editor. This time I have only 2 equations, so I'm going to change it into a 2x4 system. So the first equation is 5x minus y plus 3z equals 7. So the coefficients are 5, -1, 3, and 7. The second equation is 9x minus 2y plus 5z equals 10. So the coefficients are 9, -2, 5, and 10. When I go to solve this using RREF, the result looks like this. So 1, 0, 1, 4, and 0, 1, 2, 13. When changing this into a system of equations, I get x plus z equals 4, and y plus 2z equals 13. Z is now arbitrary, or it's a free variable as we called it in the last example. So in order to express my solution, in order to parameterize this, that is, I'm going to solve the first equation for x, the second equation for y, and get that free variable by it on the other side of the equations. And that leaves z to just be equal to z, so that my parameterized solution now appears as x is -z plus 4, y is -2z plus 13, and z is equal to z. So there's the coordinate triple that would produce, for any value I choose for z, it would produce a coordinate x, y, and z that solves my system simultaneously. And because those two planes intersect in a line, that's going to happen at an infinite number of points. So this set represents all of those points that are solutions. Now I have one last example to show you. This particular example is simply here because in the homework there's one like this, and I just want you to see what you can do in a situation similar to this. So very quickly I'm going to work this out. I have already entered it into my matrix editor, so I have the coefficients entered already, and I'm going to find the RREF of this system. I come up with something like this. So I have these decimal values for the z variable. If you'll notice, there's a little ellipses, which tells me I can scroll over to the right and see more, but I only get more decimal values. Now, the expression of your answer here in the homework, it makes a difference, and the homework asks you to basically express this using fractions. Well, here's a nice little feature in the calculator, in case you weren't aware. If you go into the Math menu The very first option is this triangle and the word frac, which means to convert the last number into a fraction. But it'll work with a matrix just as well. So if you say to convert this into fractions, then you'll get the matrix 1, 0, 12/13, and -11, and you do need to scroll over to see the rest of it, over 13. And the next row is 0, 1, -5/13, and -3/13. That's a whole lot prettier than what we started with those decimals. But at this point, we no longer need the calculator. We just do what we did in the last example to change this into a parameterized solution. So x plus 12/13 z equals -11/13, and y minus 5/13 z is equal to -3/13. And when I convert that, I get x equals -12/13 z minus 11/13, just moving the z term to the other side. Y equals positive 5/13 z minus 3/13, and z equals z. So that my parameterized solution will appear as the x is -12/13 z minus 11/13. The y is 5/13 z minus 3/13. And lastly, the z is arbitrary, so you leave it as is. And that's the solution to the system. So if you run into something like that in your homework, that will certainly be a big help to you.